and she will talk about Euler systems and the Birch-Swinnerton-Dyer conjecture. Thank you, Sarah.
So I would like to thank my co-organizers for the suggestion that here at the conference. I would also like to the Newton Institute. Oh, moment. The host has spotlighted the video for everyone. No. Right. Okay, so I'd like the Newton Institute for all the help with the organization of this conference. I mean, who has been extremely helpful. I learned in John's lecture about the Birch-Swinnerton-Dyer conjecture, and I thought then, and I think now, that it's one of the most beautiful and mysterious. It's been my dream since I was solving this conjecture. So in this way, I mean, the work of Peter and Brian has had a big influence on my work. But it turns out that Peter's work has had another influence in a very different way. Namely, I learned very recently that it was Peter who invented the REF, so the Research Excellence Framework. So I've heard that this has had a big effect, I mean, on UK universities, UK mathematics, of course. I hope that Sir Peter gave a thought for the poor souls who would have to do all the assessment. I mean, it certainly is clear, thanks to his invention, what I will be doing in the next few months. So before I go back to speak about mathematics and the BSD conjecture, I want to tell a brief story about my memories of Sir Peter. So I met him when I was a graduate student, and he offered number theory seminars and then later come to the pub with us. And the pub was actually only down the road from the Mathematics Institute, just a few hundred meters. But Peter suggested that he would drive there and that he would give me a lift. I was a bit puzzled, and I was even more puzzled when he didn't drive just down the road to the pub, but when he made a massive via the motor, because it turned out that he still had a sports car.
Yeah.
So he told me at the time that his wife didn't enjoy it very much when he drove very fast. Certainly didn't mind. So yeah, so that is my favorite conjecture of Sir Peter. I should stop the video here. Okay. Right. So let me now talk about the Birch-Swinnerton-Dyer conjecture. So the title of my talk is Euler Systems and the BSD conjecture. So let me, and to summarize, right, so the was already mentioned in the previous talks, was formulated in 1965. So impressively on the basis of numerical experimentation. So it says the following. So if you take an elliptic curve over Q, so and we write L of ES for the Hart function of the elliptic curve. So then the rank of the group of rational points on the elliptic curve is given by the order of vanishing at the point s equals 1 of the L function. So in other words, it predicts a misrelation between the rank of the elliptic curve and the properties of the L function. And we call this order of vanishing the analytic rank. Right. So there are many generalizations. So, I mean, one can very easily formulate deconjugation. So what's an abelian variety? Well, it varies as Jacobians of algebraic varieties over Q. And one can formulate a abelian conjecture for abelian varieties over number fields. So for example, for elliptic curves, I think some of them, but these here. So let's curve. Breakthrough of coats and wires in 1977. So they proved the BST rank 0 complex multiplication. So then the next big step was to Kolyvagin. And the results were later reproved in a different way. So they proved the BSD conjecture when E modular elliptic curve and the analytic rank is 0. So of course now we know, I mean, thanks but at the time of Kolyvagin's work, it was a conjecture. Right, which is due to Birch. So that was proven in 2015. So they proved the BS an equivariant version. In analytic rank 0. So equivariant, I mean, when an elliptic curve is twisted by a two-dimensional Ordartian representation. So these are the main BSD conjectures. So and let me emphasize that to make a mark. So if we have an elliptic curve over Q and the analytic rank is bigger than 1, then the conjecture is. And it turned out that Sir Peter was not very optimistic that it would be solved. I mean, David told me that he once asked Sir Peter at a college dinner whether he expected the conjecture to be proven in his lifetime. And Swinnerton-Dyer replied, "Not in your lifetime, young man." So he was not optimistic that this, I mean, good thing. And then, so what I want to do today, so I re-explain the strategy of Cato and of Bertolini, Darmon, and Roger for proving cases of the BSD conjecture for elliptic curves, and then we'll discuss how one can generalize it to abelian surfaces defined over Q. It arise, for example, over imaginary quadratic fields. So I want to discuss the case of abelian surfaces and elliptic curves. Imaginary quadratic fields. Okay, and let me just say, I mean, that this has been and we are quite happy that we finally seem to be results. Right. There's a to a strategy in rank. To begin with, I want to put BSD conjecture into a slightly more general context, namely in the context of peer representation. So let me make some peer representation of the so this is a finite dimensional QP vector space. It's a continuous action of GQ, which is unramified outside a set. So these in number 3, some examples in it. So let me now say that attached to such a periodic representation, one has an L function, which is conjectured meromorphic or continuous of the complex plane. Okay, so here are examples. Here are some examples. So when V is just a trivial representation, then the L function is just the Riemann zeta function. So if V arises as a tape module of an elliptic curve, so in other words, is QP tensored the inverse limit of the P to the n division point of the elliptic curve. So this is dimensional, which I generally write as VP of E. Then the L function is just the L function of the elliptic curve shifted by 1. And more generally, we have periodic representations attached to modular forms. So the F is a modular form or equal to 2. Now, attached to such a position, we have a Selmer group. We have these of V over Q. So this here is a subspace of the first Galois cohomology group, which is cut out by local condition. Sense, we should think of the Selmer group as a generalization of the Mordevais group attached to an elliptic curve. So if we take the rational points on the elliptic curve and we tensor it with QP, then one can show that this injects into the Selmer group. It is conjectured that the kernel is very small. One has a similar result for abelian varieties. Similar for abelian varieties. So called the illusion star. Now Bloch and Kato have formulated the following conjecture. Namely that the order of vanishing of the L function representation point equals 1 should be given by the dimension of the Selmer group as a QP vector space of V action of GQ. So this here is usually 0. So it turns out that this conjecture is very closely related to the Birch-Swinnerton-Dyer conjecture when V arises from elliptic curves. So what Kato did, so he proved the Bloch-Kato conjecture of E, then the L function at the point S equals 1 does not vanish. And then by star, because the group of rational points is basically included in the Selmer group. So by star, so this implies BSD in analytic rank 0. So when the analytic rank is equal to 0. I see that this is difficult to see. Let me just try it. Yeah. Okay, can people hear me? Right. So how did Kato prove the Bloch-Kato conjecture? Well, the main tool for his proof is what is called an Euler system. So it's an Euler system, which is an object or an idea which was first discovered by Colli-Wagen. So let me write down what an Euler system is, I mean, at least roughly, and I'll follow the definition as given by Kato, which is somewhat more general than Colli-Wagen's original definition. So an Euler system for V is a collection of cohomology classes so Zn indexed by the positive integers, and the class Zn lies in the first Galois cohomology group of the absolute Galois group of Q adjoint mu n with values in V, which satisfy the so-called Euler system norm relations. As n varies. So the idea here is that as n varies, I mean, there are maps, I mean, so-called co-restriction maps, I mean, arising from the fact that the cyclotomic fields, I mean, give Galois extensions of each other. And if we look at the images of the Euler system classes under these co-restriction maps, then they should satisfy certain relations. These Euler system norm relations, which in some sense mirror the properties of the underlying L function. So the point that these Euler systems are important is the following result. So we have the so-called Euler system machine. Which is due to Kato and Rubin. So if we have an Euler system and the bottom class of the Euler system is non-zero, and some technical hypotheses are satisfied, so then the Selma group of V is equal to 0. So in other words, Euler systems are extremely powerful tools for controlling the size of Selma groups. So the main steps in Kato's proof are the following. So the first one is to construct an Euler system. So which I call Zn for the representation Vp of E. And then the second step is to relate the bottom class of the Euler system to the value of the L function at the point s equals 1. And such a relation is called an explicit reciprocity law. So once he had these two results, and he knew that the L function did not vanish at this point, he could deduce that the bottom class of the Euler system wasn't 0. And hence he could use the Euler system machine to bound the Selma group. So this was the strategy for proving the BSD conjecture in analytic rank 0. Now, what is an essential ingredient in the proof? So is that the elliptic curve is modular. So what does this mean? It means that the elliptic curve corresponds to a modular form of weight 2. So this the modularity of elliptic curves is known thanks to the work of Wiles. So how did Kato use this? Well, it was extremely important, both for the construction of the Euler system and in the proof of the explicit reciprocity law, that if we look at the dual of the representation attached to the elliptic curve, that this is a direct summand of the first étale cohomology group of a modular curve base change to Q bar. Right, I mean, I'm not going to say here, I mean, with which coefficients I'm working. I mean, the main point is, I mean, that it is the étale cohomology of a modular curve, because this means that Kato could use the geometry of the modular curve to construct the Euler system. So this is as much as I want to say about Cato's work. Should maybe mention that the work of Bertolini, Damon, and Roger is also based on this general strategy. I mean, to realize the elliptic curve, I mean, in the entire cohomology of a modular curve, and I mean, then to construct a new Euler system from that. Right, what I now want to discuss is what happens when we try and generalize this strategy to abelian varieties. And we will see that there are many things which do not generalize very easily. Okay. So this is the next section, the case of abelian varieties. Right, so the first question is, I mean, is there some analog of the modularity conjecture? And the answer is yes. So this is called the paramodular conjecture. So which is due to Brumer and Kramer. So which roughly says that abelian surfaces over Q of general type so that these should correspond to certain genus 2 Siegel modular forms of weight 2, 2. Right, so and this correspondence should go that the p-adic representation attached to an abelian surface should correspond to the dual of the spin representation. Oops, a moment. VP spin dual of some Siegel modular form attached to A. Okay, well, what's a Siegel modular form? So a genus 2 Siegel modular form is an analog of a modular form for the group GSP4. Okay, I mean, if you haven't seen Siegel modular forms, I mean, just think of them, I mean, as some kind of analog where GL2 is replaced by the group GSP4. So, and another way of thinking about them is that they are global sections of certain line or vector bundles so on Siegel threefolds, so which takes the place of modular curves. Okay, so this is the generalization of the modularity conjecture. I mean, let me make a few remarks. So firstly, I mean, so Berger and Klosin so they proved this conjecture so when F is of Saito-Kurokawa type, then there are results of Carey and Thorne so they proved many cases of the conjecture. So for when the abelian surface arises from an elliptic curve defined over an imaginary quadratic field, and then there are also recent results of Boxer, Caligari, G, and Piloni. So they proved some version of potential modularity. For abelian surfaces. Okay, so we are going to assume this conjecture. So we are going to assume that our abelian surfaces correspond to genus 2 Siegel modular forms of parallel weight 2. Now here's the first main problem. So even if we assume even assuming the paramodular conjecture, so the periodic representation attached to A is not a direct summand of an étale cohomology group of the Siegel threefold. So instead, what happens is that it is the periodic limit of representations which arise as a direct summand of the étale cohomology. So VP of A, which is the same as VP spin of FA dual. So this is the periodic limit So it is the periodic limit of the spin representation of some Siegel modular forms F. So where F has weight K1, K2, where K1 is greater or equal to K2 is greater or equal to 3. So these representations, so they do appear so as a direct summand in the H3 étale of a Siegel threefold. So in other words, the problem is that the weight of the Siegel modular form attached to the abelian surface is too small. So, and in this sense, we should think of this Siegel modular form as being as corresponding to a classical modular form of weight 1, because this is the same phenomenon. I mean, there the Galois representation attached to a weight 1 modular form is again the periodic limit of representations which are attached to modular forms of higher weight, which appear in the étale cohomology of a modular curve. So this here is similar to weight 1 modular forms. Okay, so this is the first problem in constructing the Euler system for A. So how do we do this? Strategy for constructing an Euler system for A. Well, step 1 is to use geometric methods so to construct an Euler system, which I will call ZNF, for n greater or equal to 1. So for the representation Vp spin of f, so for f is of weight k1, k2, where k1 is greater or equal to k2 is greater or equal to 3. It turns out that this can be done generalizing the methods of Cato and of Bertolini, Damon, and Roger. But of course, we are in the wrong weight range. So this is then step 2. So we use a periodic limiting process to obtain an Euler system for which I will call ZNA. So for the representation VPA. So and this method was inspired by the work of Bertolini, Damon, and Roger on the equivariant BSD conjecture. So where they get the equivariant part, I mean precisely using such a periodic limiting process for weight 1 modular forms. So and we were able to carry out, I mean certainly the first step of this strategy. So this is joint work with David and with Chris Skinner. So, and that was completed in 2016. So this is part 1. So, and with part 2, this is work in progress. So this is joint work with David. Okay, so at least in principle, I mean, assuming we can complete the second part, we obtain an Euler system attached to an abelian, to a modular abelian surface. Now the problem that we need to solve, so to get at BSD, so we need a relation so between the bottom class of this Euler system attached to the surface and the value of the L function. So we need to prove an explicit reciprocity law. And this is where a lot of the difficulty did lie. So the idea was fairly clear, namely to again use periodic variation. So in other words, we first would want to prove a relation. So of the class Z1F, so where F has weight, well, K1 and K2 greater or equal to 3. So two values of the spin L function of F. Well, we will see that this here was a little bit overly optimistic, but I mean, this was the general idea. And the second step then to use a periodic limiting process. So periodic limiting process to deduce a relation between the Euler system class, the bottom Euler system class attached to A, and the value of the L function of the abelian surface. Okay, so here's the problem. So we need a relation so between the Euler system on the one side and values of L functions on the other side, which deforms periodically. And this turned out to be very difficult. I mean, there is a tool for this. I mean, certainly on the side of the L functions, which is called a p-adic L function. So it's a p-adic L function, which is a p-adic analytic function which interpolates certain values, so-called critical values of the complex L function. But there were two problems with this. The first one was the construction of a p-adic L function. And the second one was to prove such a relation and to show that this relation would deform p-adically. And we were actually stuck on this for over 2 years. And we were stuck very precisely until the beginning of November 2017, when David and I attended a talk by Vincent Piloni in Princeton. And it was clear within a few minutes that the theory that Piloni had developed was the missing piece that we needed to make progress on this problem. So here's the theorem which addresses the first problem, namely the construction of a suitable p-adic L function. So a first version of the theorem, so it was proven in 2019 together with David Piloni and Skinner. And David and I are currently working on a more general form, which is what we need for the applications to BSD. So a sort of stronger version is in progress. So which is as follows. So let F, I call it F double underline, which will depend on two parameters, kappa 1 and kappa 2, be a Coleman family through the Siegel modular form attached to the abelian surface by the paramodular conjecture. So, well, what's a Coleman family? Well, it is a family of p-adic Siegel modular forms, I mean, with two weight variables. And if we specialize those at weight 2, 2, then we recover Fa. So, and we assume some technical hypotheses. So then there exists a 3-variable p-adic L function. So which I will call LP spin. So which will depend, so two of the variables are just the weight variables. And we have an additional variable, which I call lambda, which is a cyclotomic variable. So such that for K1 and K2 greater or equal to 3, which are close to 2, 2, so close to the point 2, 2, and when J is in the critical range, which means that J is between K2 minus 1 and J and K1 minus 1, K1 minus 1. So we have the following interpolation property. Namely, if we evaluate the spin p-adic L function at these points, K1, K2, and J, so then up to an explicit non-zero factor, we get the value of the spin L function of the Coleman family specialized at K1 and K2 and evaluated at J. And this here divided by a certain period. So, and these values are the critical values of the L function. So in other words, you really have a three-variable periodic analytic function which interpolates the critical values of the classical form in the Coleman family. Now we have a further result. So if the eigenvariety is smooth at the point corresponding to the Siegel modular form Fa, then the periodic L function evaluated at the point 2, 2, 1 is just the value of the L function of the abelian surface divided by the period. So this here is a slightly annoying assumption. I will say something about that later. Okay, so we now have the Euler system, which varies in periodic families, and we have the periodic L function. Well, here's a theorem relating the two. So this is joint work with David, which we completed a year ago. So let K1 and K2 be integers at least 3, and let F be the specialization of the Coleman family at K1 and K2. So then the bottom Euler system class for the spin representation attached to F is related to a non-critical value say of the periodic spin L function. Okay. I mean, so in this sense, I mean, our previous conjecture, I mean, that the Euler system should be related to values of the complex L function was too naive. I mean, we only get here at non-critical values, so which do not correspond to anything in the complex world. However, so, okay, I mean, we will see that this is still sufficient for our purpose. Should maybe mention, so by Perrin-Riou, one can show that this relation deforms periodically. So this relation deforms periodically. So what does this mean now for our application? I mean, when we evaluate at the point 2, 2, 1. Well, we have the following corollary, which is joined with David and which is work in progress. So, namely, we let A be a modular abelian surface over Q, which corresponds to a Siegel modular form of parallel weight 2. So, and we assume so that the eigenvariety so is smooth. So at the point corresponding to Fa, if the value of the L function of the abelian surface is not equal to 0. And I should say, moment. And we assume some technical hypotheses. Right. Now, if the value of the L function is not equal to 0, then the rank of the abelian surface is equal to 0. Okay, so how do we prove this? Well, it is a fairly easy consequence of what we have done before. So from the theorem above, say from above, and a periodic limiting process so we get that the bottom Euler system class of the Euler system attached to the abelian surface is related to the critical value of the periodic L function, which turns out to be the value of the L function of the abelian surface at 1. So hence we deduce that if this L value is not equal to 0, so then the bottom Euler system class is non-zero. So via the Euler system machine, so we deduce that the Selmer group of the periodic representation attached to E is equal to 0. And since the group of rational points injects into the Selmer group, we deduce that the rank of the group of rational points on the abelian surface is equal to 0. So since A of Q tensor QP injects into the Selmer group. So this is precisely the same argument that Cato used. Right, so let me conclude with a few remarks. So firstly, if A arises from an elliptic curve over an imaginary quadratic field, so over an imaginary quadratic field, so then the smoothness of the eigenvariety is implied by a conjecture of Caligari and Maser. So my second comment is that we can, in a similar manner, prove, this is also in progress. So we believe we can prove an equivariant version of the BSD conjecture. So BSD, so in analytic rank 0, so for A twisted by a two-dimensional odd Artin representation, so this is work in progress together with David. So, I mean, we're currently in the process of writing up these results. Hello.
Sorry, no, that's it. Nothing.
Right, so we are currently in the process of writing up these results, but something that is already written up. So this was work which we completed last year, is that we can prove many cases of the Bloch-Cato conjecture. So in analytic rank 0, So for the spin representation, so attached to a genus to Siegel modular form, but where the modular form is of weight K1 and K2, so where K1 is greater or equal to K2 is greater or equal to 3. So in these cases, I mean, we do not obtain any information about the Birch-Swinnerton-Dyer conjecture. I mean, there we really need to deform to parallel weight 2. So let me stop here. Thank you.
So thank you, Sarah. Are there any questions?
Can you
Ollie?
say something about the non-critical value you get?
Yeah, one moment, let me just try and turn this here off. Don't know what to do with this. I think David is just coming, one moment. Oh. Right, I hope that I want to turn this here. Yeah, good, why don't you ask your question, Barry?
Yeah, the non-critical value that shows up corresponding to your fairly geometric Euler system. Can you say anything more about it? I mean, where?
Yes, I mean, so I did not really talk about for which twists we can construct the Euler system classes. I mean, we construct those for twists in a range which has empty intersection with the critical range. So these are the values between, for J between 1 and K2 minus 2. And it is then precisely those values of the P-Degrelle function, I mean, where we get the relation.
So the reason why it's non-critical is you've twisted by the wrong character, is that it? Or? Yes,
I mean, we can only construct the geometric Euler system classes, I mean, for the twists, for a range of twists, I mean, which is disjoint, I mean, from the range of critical twists. And that makes the proof then a bit delicate because one has to go back and forth, I mean, between the critical and what we call the geometric range of twists.
Thanks, thanks.
Which is true for Cato as well.
David, why don't you come here? Yeah, as David just put it, that is true for Cato, in Cato's construction as well.
So I wanted to ask you, Sarah, can you say a few words about how the geometric class is constructed in the geometric range? I apologize if I'm asking you to repeat something you already said, but there were moments when I didn't catch you. The internet was a bit
well, how we construct them.
Yeah. I mean, sort of just give a bit of a description of what goes into the construction.
Ah, okay. Well, I don't think you missed anything there. I didn't actually say anything about it. What we do is we consider the embedding of two modular curves into a Siegel threefold. I mean, basically coming from the natural embedding of GL2 times GL2 into GSP4. And we push forward the exterior cup product of two Eisenstein classes into the Étale cohomology, I mean, of the Siegel threefold. And this is the bottom class of the Euler system. I mean, to get classes over the cyclotomic extensions, I mean, that's a bit more complicated. I mean, one has to change the embedding slightly, but the basic ingredient is this embedding in the Eisenstein classes.
We call these classes lemma-Flach classes because the class in motivic Kermode studied by Francesco Lemma in his thesis. He computed the complex regulator of this class, and we kind of took it and ran with it and computed its p-adic regulator instead.
Very nice. And so your result that you alluded to before, where you had a twist by an odd Artin representation for dimension 2, that came from doing something similar with Bales and Flach classes, so to speak.
That is correct. I mean, what we do is, I mean, there we use a different Euler system, I mean, for GSP4 times GL2, where we again embed GL2 times GL2 in it. We only have one Euler, so we take just a cycle class on one GL2 factor and an Eisenstein class on the other GL2 factor and push them forward along the natural embedding. And it turns out we can again extend this, I mean, to a full Euler system. I mean, that was done by well, one of our Arizona project groups. Who was it? Sue, Ryotaro, and
Sakamoto.
And Sakamoto, yeah. So, and we have been able to prove a relation, I mean, to periodic L values, I mean, in precisely analogous way. I mean, the computation just goes through.
And if you now wanted to prove a result for a tensor product of two odd arts and representations, where, you know, I guess you don't have the full Euler system, but do you have enough to kind of get finiteness of model V or so?
Yes, well, we do indeed there. I mean, we have a sort of cycle class. I mean, we push forward into GSP4 times GL2 times GL2. I don't know whether we can prove something there. I haven't really thought about this case. David, do you have any opinion on that?
The problem is to relate anything to L values, you would need cases of the orthogonal Gann-Gross-Prasad conjecture, which are not known in general. Maybe if one of your arts and representations was dihedral type or something, it's known, but the general case is not known.
Right.
Yeah, but in in principle, I mean, there should be something there, yes.
Yeah.
So, Barry, do you have any idea about your conjecture with Frank? Sorry, you're mute at present.
I was going to ask you. I mean, you mean an idea of how to prove it, or an idea of how to generalize it?
Well, for us, it would be ideal to have an idea how to prove it.
No, I don't have any, but I can try to think about it. Do you, going back, returning the question to you, do you have any ideas about GSP6?
Well, that is a very interesting case. So one of my PhD students, Antonio Cauchi, together with Joaquim Rodriguez, they constructed classes in the motivic homology of the Shimura variety attached to GSP6. And they can construct them over the cyclotomic extensions. And in the p-cyclotomic direction, they have proved the norm relations. But our formalism for proving the tame norm relations does not work. I mean, this is extremely frustrating. I mean, we need a local multiplicity 1 result there, which simply doesn't hold for GSP6. So
GSP6 are very complicated, aren't they? I mean,
yeah. I mean, it does seem conceivable that one could construct a periodic L function, I mean, using the methods we have developed in this case. At least, I mean, I don't really see any reasons why one couldn't. But of course, it would be of limited use. I mean, if one doesn't have the tame norm relations. So, yeah.
We also rather suspect that that these classes are probably zero if you project them to most Hecker eigenspaces. They should only somehow survive in Hecker eigenspaces of some specific form. Like factorial lifts from some subgroup of the algorithm.
Well, I believe that Antonio is still thinking about that, but I don't know about the most recent progress on this.
He's speaking about it at a conference tomorrow morning.
Oh, is he?
There's another conference happening in parallel with this week, and Antonio is speaking.
Right. Okay. More.
I think maybe Wednesday morning.
Thank you. Wonderful lecture.
Thank you. I apologize for the technical problems. I only realized at the last minute that in my office upstairs, I mean, the internet connection was very dubious. And so I had to rearrange everything at the very last second. So that was part of the problem. So, yeah.
So are there any more questions?
I think there was something in the, if you turn the, no, okay, that was just.
Yes. So let me thank Sarah very much for her very interesting lecture. And I guess that's it for today. So we meet again at 2 o'clock tomorrow. And thank you, everyone.
Thanks.